Good morning, everyone. I'm glad you're here. We're going to talk more about Lidar today. As you saw previously, Fish and Wildlife was talking about aerial Lidar and Geiger mode and linear mode and so on. This time we're going to bring it down to street level, collecting high-density Lidar using mobile assets. My name is Paul Bader. I'm a certified photogrammetrist. I'm also a PLS in North Carolina, South Carolina, and Virginia. And I work for a company called GPI. We're involved a lot in LiDAR and the statewide initiatives. So we collect LiDAR from aerial means and mobile means and static means, and we can combine all these data sets together and produce what we need to produce. In this case, I'll be talking about asset inventory, being transportation assets, from signs to edge of pavement to guardrails, and how we collect this data using point clouds. All right, so asset management is an important component of all infrastructure projects. DOTs want to know where their assets are, what kind of shape they're in, and of course it's got significant cost maintaining and updating all of this information. Signs have a life to them. They want to know their reflectivity values, when to change them, when to not, and so they need this information, and it's used with mobile LiDAR, not just signs, but road conditions, pavement conditions, rutting, and then cracks in the pavement. So it's all measured using mobile LiDAR means. So it minimizes the field work. You don't have to put surveyors in the middle of the highway or folks hindering commuters and traffic. And of course, all of this data can be reviewed in the office without having to go back to the field, and then you keep on updating it and for changing conditions. So the applications are, we can do automatic road marking extraction. We can extract all of the paint stripes on the road. Of course, the sign inventory is big, and then the sheeting replacement, this being the actual sign face itself. And of course, reflectivity studies and analysis, where at night we can shine a light and give them reflectivity values for all of these signs. And we're collecting physical features, planimetric features, from poles to lamps and barriers and curbs and gutters and catch basins and edge of pavement. You name it, we collect it with these point clouds. And of course, all of this data is now placed into a database, and then you can imagine, all of the highway assets that they own, all in a nice compact database. And of course, pass and fail maintenance management systems. DOTs, some DOTs will go and collect video, georeference video, all of the roadways, and then decide on what to maintain and when, and prioritize depending on the assets that they have. And of course, all of this is tied to their budget. They can say, this year I'm going to change this section of the guardrail because it's in poor conditions, or it can wait another year for something more important or more urgent. So you can imagine it helps them out with their management system. Key factors, which, can we do it from the air? Yes, we can do some aspects from the air, but obviously safety, is number one. We got to keep folks off the highway and then do our job efficiently. Same thing with accuracy. How accurate is the data? Do we want to be accurate to engineering level accuracy, or do we want it to be within, half a foot or so? You can imagine with the proper ground control, we can literally measure the thickness of the paint stripe with this data. It's very accurate. And then, of course, coverage limits. When you're doing mobile LiDAR, we can, drive each lane, but then beyond the edge of pavement, we can go maybe about 40 feet or 50 feet, depending on the height of the mobile LiDAR sensor on top of the van. So you can't go possibly for a big right-of-way to right-of-way, but maybe about 50 feet beyond the edge of pavement. And of course, it reduces the schedule. We can do this fast and then what kind of details do we need? Do we want imagery to go with it? And we'll see some examples of that coming up. So this is the cycle of any of these projects. You have to have ground control. You gotta send surveyors out in the field, set panels. You guys have seen panels on the side of the road. There could be little chevrons or a cross, and then there's a PK nail at the tip of the panel or the center of the panel. And the surveyor goes out and measures an XYZ coordinate for that panel, and that's how we georeference the LiDAR data to the control network and then tie it in so we can all be working on the same data. And then the second cycle is data acquisition itself. What are the challenges to acquire mobile LiDAR? How do we do it? And what kind of means do we use, and so on. And then processing this data. These are millions and millions of points and gigabytes of terabytes of data. So how do we process it? How do we get there? And then what do we do with it? What do we extract out of the data? And then finally, the 3D product. All of these pulses have an XYZ coordinate. And then so how do you deliver it? What format? Do you deliver the entire point cloud? Can your systems handle it? And then so that's basically the cycle of a 3D LiDAR project, whether it's from the air or mobile or static. So the first, we're going to talk about control first of all, and you'll see that the where we're at, based on that bubble on the top right corner there. So first thing is we got to recover the existing NGS monuments. From, let's suppose we're collecting assets for this section of the highway. Surveyors would go in and see where these existing monuments are to tie to. And then you're going to establish your vertical and horizontal control based on these NGS monuments. So this is the recovery phase, basically. And then, of course, you got your horizontal and vertical networks, depending on which state you're working in. You got to produce your data at state plane coordinate systems. And then, as you know, control is the foundation of everything we do. We can't do anything without ground control. The data can be acquired, but it'll be relative accuracy. And if we want to get down to really good accuracy, we have to tie it to a network. You can see a sample of these chevrons. That's tiny little chevrons. A lot of companies use different shapes, but we're talking about a 4-inch wide legs, and then maybe about a foot, in length. So these, obviously, we got to keep people off the highway. This happens to be a project down in South Carolina on I-526. We had to do it late at night because we wanted to shut down one lane, and this was after midnight. And then, of course, they're observing the panel on the side of the road. And in this case, this is a tiny shoulder, so it's pretty critical for these surveyors to be safe. So you GPS these control monuments or these control targets, and then you establish your XYZ coordinate. And then we'll see later on how these coordinates are going to become valuable and how you tie it to the point cloud. This is, so we set the control, it got observed, we have XYZ coordinates on all of these panels. It's time to collect the data. This is one of our 2 vans, mobile LiDAR vans. We'll get to see closer up pictures, but these sensors can emit up to 1 million points a second. Pretty powerful point cloud. And it's got a dual channel system. So you got one laser here and one laser there, and a GPS antenna on the top, and then it also has built-in these 36 megapixel cameras. You got rear view cameras and then forward-facing view cameras. So you got 360 view of all of the imagery that's collecting at the same time as you're collecting LiDAR. And then these images are georeferenced. They have an XYZ coordinate to them, so we know exactly where they fit in. And then, of course, we collect also video, georeferenced video, so you can go in and see where you are physically, geographically. And then, so these cameras are tied to the point cloud, and now you're looking at Lidar, point cloud, and photos. And of course, you can freeze the frames and then extract out a frame that's got an embedded GeoTIFF reference point to it. So you can click on that image, and it automatically takes you into Google Earth and shows you where you are too. This is a close-up of the sensor itself, and so these are the mirrors of the laser. You got the cameras, the rear-facing cameras, and of course the GPS antenna. And you can see the height of this. It's got probably about 12 feet field of view, and then so you can see. If you put them on a small vehicle, you're not going to get the range that you would get from a higher point of view. So the impact is just like driving down the road collecting data. You don't want to drive where you have traffic. We can't. You have to shut down the system if you have traffic. You have to maintain your speed. So you have a driver and a spotter and a data operator, a sensor operator. The sensor operator is sitting in the van watching the data coverage, and then you have the spotter that's telling the driver, hey, I can see a traffic down the road. You might want to slow down, or let's get ready to shut it down before we get to a standstill. So roads, conditions, construction on these roads are issues for us. And then, of course, equipment failure. It does not break down that much, but these are sensitive pieces of equipment, sensors, and so believe it or not, it does not like cold weather. Sometimes we have to warm it up in states like Wisconsin or Illinois, and where it's very cold in the morning, and then so it does not like cold weather. And then so you have to maintain them, you have to calibrate them. We have what we call a bore site calibration. We go to a certain place that we have, and then calibrate these sensors before we take on the mission. And so the daily route is planned, and of course you calibrate the camera post and pre-mission. We're collecting LiDAR and imagery at the same time. And of course you're tied to a GPS network. You're tied to 5, 6, 7 satellites at one time. You got to make sure that you have not lost your signal. And so you monitor all these conditions, and the idea here is to drive at highway speeds and collect as much as you can. Now, in good conditions, we can collect up to 50, 60 miles a day. And then, so it depends on where you are and what kind of conditions you need to be in. Sometimes we collect at night, the LiDAR, like if we're doing in an urban area where you have cars parked on both sides of the road, and in the daytime, and then we want to see the curb and gutter. Well, we can't see them because of the cars, and then so in this case, we collect the LiDAR data at night and the imagery in the daytime. It depends on what you have, what kind of conditions you have. So obviously you have the drive logs, you have the GNSS tracking, the vehicle speed. We got to know all of that, and then the potential IMU drift. This is the kind of like in the air. You're talking about the inertial measurement unit, the pitch and yaw, and the roll of the aircraft. In this case, you're talking about the movement of the van, and then of course it's got the sensor functionality on it. So we collected now the data. We have it all stored, and what do we do with it? Well, we got to start processing the data. First thing we do, obviously, is we got to process the trajectory for it. This is tied into the GPS and the GLONASS results. We can see all of these satellite logs, and then we can tell whether we have good lock or not. Of course, you got to establish your SBET positions, and then that's part of the trajectory processing. We can see the metrics of all of the data that we collected and how well the trajectory is fitting in. We talked about the sensor attitude results, which is the IMU, and then of course all of this is measured, the heading, the ground speed, and the roll and the pitch. And then all of this deviation can be exported into Google Earth. We can verify the vertical alignment between scan passes. All of these scans are overlapping each other. So if we're scanning one lane and then driving another one, so this overlap we have to make sure to account for. So you don't want vertical difference between the scans. And so it's a good indicator of data quality and trajectory results once we see. You can see what kind of deviation we're talking about here, from hundredths to a tenth. We're chasing 2/100ths of a foot. Point cloud deviation, we can set the parameters for the point cloud, and then we can see the noise. You're going to see noise, and then so cars behind you, that's noise. And so we can remove all of these objects, end up with a bare earth, basically, and physical features model. So the software automatically takes care of the noise for you, maybe about 85% confidence level, but somebody's still got to go in there and clean up the data, and that's done manually. Of course, now we have the control points. You can't see it too well here, but then you have a control point, and then of course you have a point cloud on top of the point. We can see the panel and the intensity of the image, and then so we have an XYZ value that's surveyed, and then we have a Lidar value, which is the point cloud, and then now we can pull a delta XYZ to see how well we're fitting with the control. So you got an assessment of the control points. Then we produce a surveyor report. You got in here target 1, easting northern elevation, and then this is the Lidar, easting northern elevation, and then you got the delta XYZ difference, and then you come up with a RMSE. Tiling and coverage, we want to make sure that we collected what we needed to collect. We don't have any gaps in the data. And you can imagine this data is very large data sets. You're dealing with millions of points and terabytes of data. So you have to tile it and manage the data. And it's easier to use multiple personnel staff on this data. One team can be working from tile 1 to 10, the other team can be working from 10 to 20, and then they're not gonna, it's not gonna affect the production cycle. And if issues are found during the Lidar QC, we don't have to shut down the entire project. We can say, hey, we gotta deal with tile number 2. You guys work with tile number 3 and 4, it's fine. So you can track and make sure that, if we want to know percentage complete, we can tell from the tiles that's been worked on very quickly. We got to measure the point density. Are we getting the density that we need? We can put in basically a fence on top of the Lidar point cloud, and then it gives us a value. In this case, we're averaging about 780 some points per square meter, or square foot in this case. And for mobile Lidar, we use a piece of software called Topodot. I'm not sure there are many other software, but Topodot seems to be to handle point clouds, mobile Lidar point clouds, the best what we see. And it's got all kinds of tools. It works on top of MicroStation, so you're collecting directly in a DGN environment. So of course you got to deal with horizontal misalignments. In this case, you can see, obviously this is a lamppost. You can vectorize it, you can put a symbol on top of it, and then of course we have point clouds on the base of the pole itself, and then we can see any deviation horizontally. And then of course same thing with vertically. You have all of these curves that are on top of each other, basically from the point cloud, and if they're aligning well, that means we have a good horizontal base. So you always take one scan being as your base, and it's already been proven horizontally, vertically, and then you tie the rest of these scans to it. So in this case, you can use power poles, markers, and so on. Curbing and traffic separators are good indicators as well. So in this case, you have 6 passes, and basically 6 data sets are trying to fit on top of each other. This is, you can do a cross-section, obviously, of all of this. Look at it closely in your CAD environment and verify that the ground class is actually that. How did we do on the coverage? In this case, here's the right-of-way. We have plenty of data to map from right-of-way to right-of-way. And of course, you can see how dense this data is. These are all points, so you can see the shape of the turn arrow and the paint markings. So in this case, you can do an automatic and semi-automatic feature extraction. We're collecting rumble strips, pavement markings, mowing areas. If they want to do a budget on mowing, areas, we can outline this and give them that volume, the area, I guess. Same thing with barrier walls and signs and bridge clearances, and all of that is collected at the same time. And of course, paint markings is very important in some areas too, because it's got reflectivity values too when you're driving at night and you don't have any lampposts on some sections of highways. This is an example of Lidar and line work point cloud. You can see there's some shadowing in there. Here's a big drainage. You got like a concrete drainage outlet out there. Of course, in here we're generating a tin surface. You can see the triangles at the bare earth. So now we can give you a terrain. We can give you cross sections at 5, 10-foot intervals, 1-foot intervals, whatever you need. And then in here you can exaggerate the tin itself and see for any anomalies, any irregularities. So finally we get to the 3D product. So we collected the data, we calibrated it, we tied it to a network. Now we're ready to start putting it into a database. And then of course you're collecting, here's the point cloud, here's the photo of the point cloud. If you want to collect this power pole, you can. With these assets too, we can now collect power pole line hits, for example. If you're doing PLS CAD modeling for power companies or distribution lines, if you have a transmission line and you have a distribution line and you want to know the clearance between distribution and transmission, you can easily measure that and model it. And then, so it's all done with this type of technology. We can produce, obviously, DTM files that's got all of the data in there, from physical features, planimetric features to DTMs. And so now it's all in one file, combining all the DTMs, and whether it's terrain and aerial or mobile or static. This is an example of the database that it gets created. You can select all the stop signs in poor conditions and find them, tie them to Google Earth and see where they're at. This happens to be for West Virginia DOT. Same thing with maintenance districts. They know exactly which roads they need to maintain and the conditions. You can load your Lidar data in that database as well. So now I have the overhead signs. I can see the clearance. I can measure it in 2 years from now to see if there's any movement in these signs. So in summary, we collected Lidar. Obviously, most problems can be avoided if planning and communications. We're doing this at highway speeds. Most of the work is really done in the office, not in the field. And of course, you increase safety and cost savings. You can imagine doing this in the field rather than using mobile Lidar. And that's all I have, and I'm ready for any questions. Yes?
The automatic feature extraction, what do you find is the highest accuracy rate for that, and what types of objects would lend itself to that?
Okay, that's a good question. So the question is, with automatic feature extraction, which features are best collected automatically, and which ones are causing problems? Road markings are probably the best ones for automatic. It can see them from the intensity images. Power poles are very good. Big poles, we're talking, probably half-inch or half-foot diameter or higher. You can definitely extract them automatically and place a symbol in there. Tiny, small street signs, that's got like maybe the metal leg. These are tough to extract automatically. Overhead signs are not an issue. Barriers are not an issue. It gets lost when a barrier goes under a bridge, if you want to call it. It does not know how to continue it, so it stops at the bridge abutment, and then you have to pick it up manually on the other side. So I would say 85-90% of features are automatically extracted, and then the 10% are still have to be dealt with in CAD environment. Any other questions? Edge of pavement is very easy. If it's a clean edge of pavement, if it's a irregular edge of pavement, it's going to try to show you exactly where the edge of pavement is, and then you might have some lines that are not straight, and then so you have to take care of that too in the CAD environment. Nobody wants to see a road that's doing that, even though it is. It's so accurate that it is following the edge of pavement. That's tough. Yeah, I mean, we can do it manually, I guess, from the video. We can see change of surface from concrete to asphalt, basically, and then we can put a line there showing DOT where the change of surface is, but automatically it probably cannot.
And then another follow-up question, like when we think about cost, the cost curve.
Yeah.
Are you seeing what's the cost curve look like over the next?
It keeps on going down. Yeah. So it's
Sharp, or is it kind of starting to?
It's tapering off. I mean, there's a point where you have to maintain it. But I can give you an example. In the 4 or 5, these instruments are very expensive. They're about $1.2-1.3 million a sensor. Just the van itself with the computers and all of the peripherals that you got to put on there, it's another $300-some thousand. So you're investing about $1.5 million in that van and its components. So you got to get your money out of it somehow. And then so it's usually amortized for maybe about 5 years cycle, and then hopefully you can get your money out of it by then. Maintenance is huge on these sensors, software and hardware. We pay close to $70,000 a year basically on maintenance for the sensor itself and the software that goes with it. So typically you're charging anywhere between $15,000 to $20,000 a mile for these type of assets, and then so hopefully you can recover your investment fairly fast. And manufacturers keep on coming up with bigger and better sensors all the time. And then so we find that with the aerial and the mobile. And so it's a great investment, but it pays off if you know what you're doing and execute well. And so if you're having issues and you have to go back and redrive, you just lost money. Any other questions? Yes, ma'am.
Seems to be mostly used for DOT or right-of-ways. Has it been applied for other data collection?
For mobile, no. To be honest with you, no. It's been mostly for DOTs and data collection, and it's used for engineering, obviously. So if we're if you're designing a highway and then you're going from like 2 lanes to 4 lanes, and you want to do some as-builds pre and after, that's also used for engineering purposes, not just for asset management. But it's mostly following roadways, so at least with mobile. But from aerial, obviously, we're doing statewide, like you saw, with the Geiger mode in North Carolina, floodplain, and so on. But for mobile means, it's mostly roadways. Any other questions? Well, I appreciate your time. I hope this was informative. Thank you so much.